Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Let me introduce myself. My name Andika Wisnujati, come from Universitas Muhammadiyah Yogyakarta from Indonesia, and another author in our research. I would like to present with the title Analysis Computational Fluid Dynamics and the States of Ballast Loading on a Passenger Ship's Prototype. Here, our table of contents: first, introduction, and then the second, objective of our study, and the third, methodology, and the fourth is the results and discussion, and the last one is conclusions and recommendation. In the computational fluid dynamics, or CFD, is a branch of the fluid mechanics that use numerical analysis to analyze the fluid flows. In here, we use CFD in various fields such as aerodynamics, automotive design, and the maritime engineering. In maritime engineering, CFD helps in optimizing of hull design and predicting the behavior of ships in water. And then understanding the fundamentals of CFD is crucial for analyzing fluid dynamics in ballast loading scenario. Then the ballast basics. In the ballast loading involves adding water to ballast tanks to maintain the ship's stability. You can see in the figure 1A is a ballast load, and then in B is a full load. Our background in of this research stems from the critical importance of effectively managing ballast loading on passenger ships to ensure the stability, safety, and operational efficiency during the voyages. Our goal, the objective of this study is to analyze the effect of the ballast loading on the fluid dynamics of a passenger ship's prototype with the variable of speeds 1, 10, and 20 knots. The second one, by leveraging the GFD, this research aims to enhance understanding and optimize the management of ballast loading on passenger ships, thereby addressing the limitation of traditional methods and advance the state of the art in maritime engineering practice. The methodology of this research. The first is setting up the CFD simulations, involves creating a computational model of the ship and defining the fluid's properties. And then our boundary conditions, including the inlet and outlet flows, need to be accurately defined for realistic simulations. And then the mesh generation is a crucial step, and then the proper setup of initial conditions and solve the parameter is essential for successful CFD analysis. And then our results. The first is a design prototype. First, the ship's geometry is imported into Autodesk Inventor 360, where it is prepared for the simulations. And the next, the simulation setup is configured, including specifying boundary conditions such as inflow velocity and etc., and the factor relevant to the ship's operation. Here, our modification of the side ship, we can see in the figure 2 in the design of prototype of passenger ships. After establishing the boundary conditions, we run the numerical solver over the computational grid to perform the CFD simulation and analyze the results in detail. And then this is all of the design of the prototype ship's passenger in here, figure 3 and figure 4. And our results of the velocity magnitude using CFD with the result of CFD velocity, we can see in figure 5 the fluid flow condition and velocity magnitude on the passenger ship's prototype in the ballast loading state at a speed of 1 knot. The simulation results carried out with a ship speed of 1 knot, we can see that the resistance of the passenger ship prototype is around 30 until 50 centimeter per second. And then the obtained fluid flow speed range from the minimum of 0 to a maximum of 83 centimeter per second. In this condition, the level of friction on the ship's hull doesn't affect its condition. And then in the figure 6 in the left, and the speed of 10 knots, the passenger ship's prototypes exhibits resistance of approximately 200 until 400 centimeter per second, while the fluid flow speed reached a minimum of 0 and a maximum of 766.921 centimeter per second. And then in figure 7 we can see the variable of speed 20 knots. We can get the resistance between 400 until 800 centimeter per second at a ship speed of 20 knots, and then achieve a minimum fluid flow speed of 0 and a maximum of 1504.56 centimeter per second. So in a CFD simulation of a ship, the velocity magnitudes can vary significantly depending on factors such as hull shapes, propulsion system, and environmental conditions. Near the ship's bow, the velocity magnitude tends to be higher due to the forward motion of the vessel and the converging flow of water around the hull. And then our conclusion and recommendation. The study concludes that CFD is a powerful tool for analyzing ballast loading effects on passenger ships. And then the key findings include optimal ballast configuration that enhance safety, performance, and fuel efficiency. Then the third, the study provides actionable recommendation for maritime engineers and ships designers. For the future research, we can direction include the exploring advanced CFD technique and real-time ballast management system. Thank you very much for your attention, and if you have any question, please send to my email Andika Wisnujati at umy.ac.id. Thank you and wassalamualaikum warahmatullahi wabarakatuh.